Alright, time for you to practice some more now that you've been over those problems. The next section is called More Practice with Integrals, and there are 5 problems. Some that are similar to what we just did, and some of them that will include some applications. Take some time to work these out, and then unpause the video, and you can come back for a detailed explanation of the solutions. Alright, welcome back. Alright, so a little bit more with area here. The integral from -3 to 0. So, from -3 to 0, here's the left boundary at -3, the right boundary at 0, and here's the x-axis, and here's the function, and hopefully you recognize this as a trapezoid. And therefore we use the area formula for a trapezoid. 1/2 height times base 1 plus base 2. Okay, 4.5. 4.5. Alright, the next one is the integral from -5, here's -5, to -4. And this is a triangle, but it is entirely below the x-axis. Therefore, it should be a negative area. And so what I did there is I had said 1/2 base times height, and I just used a negative height to give me the negative area. So this area right here is -1. What about the area from -5 to -3? So now I have both this triangle that's below the x-axis as well as this triangle that's above the x-axis. And if you think that they look the same, you're right. This has area +1 and this has area -1. So what is their combined area? It is 0. They cancel out. The integral from 2 to 4. Here's 2. Here's 4, and once again here we have 0.5 as this area, but -0.5 for this area, and once again we get an area of 0. What about the integral from 0 to 2? So this one's a little bit tricky, and you have to use some geometry. So this area, So the trick for finding this area is the fact that it's below here a semicircle. So if we close off this rectangle here, that would have area 2. Okay, just a simple rectangle. But I want to take away now, so I'm going to take away the area of that semicircle. And if you look at the semicircle, it has a radius of 1. And so the area of the circle would be pi times 1 squared. 1 squared. And because it's half of a circle, I would divide that by 2. So that's the area. That's what's left, is 2 minus the area of that semicircle gives us that area down here and the curvy part right there and right there. Okay, and leaving it as 2 minus pi over 2 is just fine. The next integral goes from -5 to +4. So from this side to this side. And we can find all of that by just adding up all of the areas that we see. Okay, so here I broke it down for you. So we had the area from -5 to -3, which we calculated back here. Okay, that gets us to this point. And then we have the area from -3 to 0, which we calculated up here. And that gets us to this point. Then we have the area from 0 to 2, which we just calculated back here. And that gets us to this point. And then we have the area from 2 to 4, which we calculated back here. and that gets us all the way to the end. So if you combine all four of those numbers, then you get this lovely answer right there. Down at the bottom, we have the integral from -3 to -3. Haha, that's 0, no matter what. And then finally, the integral from 0 to -3 of 2f plus 1. So here a couple things are going on. One is that you can use the linearity property, split it up. Split up the plus and also take out the 2 coefficient. But you will also notice that the 0 and the -3 are out of order. So I need to reverse them, and when I reverse them, I change the sign. And since I know what this is, right, so this one we calculated where? Oh, the first one, 4.5. But what about this? Well, hopefully you didn't fall for it again. Here, you want to envision the graph of 1. Okay, so here's y equals 1 from -3 to 0. Okay, so it's this rectangle right here, and that area is 3. Okay. So -2 times 4.5 minus the 3 makes -12. Number 2. Here we're going to do a little drawing of the graphs. So the function is 4, and we're going from 1 to 3. Okay, from 1 to 3, and of course the area there, 2 times 4 is 8. The second one. So this is a line that starts at 2 and has slope 1/2. That means I'm going up 1 and over 2. And so there's the line. And my boundaries are on the left, my limit is 0, and on the right, my limit is 4. And I'm above the x-axis here, so this is a trapezoid. And therefore, I'm going to do 1/2. And then the height of the trapezoid is 4. Okay, the height here is the distance along the bottom, right here. And then the bases are 2 on the left and 4 here on the right. So 2 plus 4. 2 plus 4. And so 6 times 4 divided by 2 is 12. So that's that area. Third one. Hopefully you recognize this as a circle. A circle with radius. What's the radius? That's right. The square root of 16. Square root of 16, which is 4. So this time my circle goes like this, and my boundaries are 0 to 4, and above the x-axis. And so here I have pi r squared, pi times the radius squared. And then because this is a quarter of a circle, I'm going to divide that by 4, and that gives me 4 pi. 4 pi. Alright, down here at the bottom, another absolute value. If you draw the line x minus 1 and just flip the negative part of the graph to the positive side, you'll see a graph that looks like that. And my boundaries are 0 on the left and 3 on the right. And so everything's above the x-axis. I'm looking for the areas of those two triangles. And I have 0.5 here, that's a half. And this has area 2. And combined, they make 2.5. Oh no, what about sine? This is sine plus 2. And the limit goes from 0 to 2 pi. So let's do this. the first trick that I'll use here, so you could shift the sine graph up 2 spaces, but let's use the linearity property. Let's split it up into 2 integrals. That way we can focus on each one separately. Because you might remember what the graph of sine looks like, right? So if I make my y-axis here go by 1s, and if I make my x-axis, let's make this so a period of sine is 2 pi, right? So it takes 2 pi to go all the way around the unit circle, and so and that's 1 pi right there. So let's visualize these 2 functions separately. So the 2 is of course just a constant, right? And the integral from 0 to 2 pi. So that would be a rectangle, and this rectangle, right? So I'm looking at this integral right here. This rectangle would be 2 units tall. So 2 times, and then 2 pi is how wide it is, and so that has area 4 pi, so equals 4 pi. So what about the sine? Oh boys, well, let's draw the sine graph. So let me change colors here. Go to purple. So remember how sine looks. So sine starts at 0, and by pi over 2 it's up at its highest point at 1, and then it goes back down to 0 at pi, and then to -1, and by 2 pi it has made a full cycle, okay, a full wave. So let's analyze this area. Well, so here we have part of this that has positive area right there, and part of this that has negative area here. And what does your intuition tell you? That's right. They have exactly the same but opposite areas. And therefore, this integral has area 0. And therefore, our combined areas is just 4 pi. Not too bad, huh? Last one. 1 over x. So this one you might be a little bit less familiar with. I'm going to just plot a few points here. So for instance, when x is 1, we get the 0.11. When x is 2, we get a half. When x is 3, we get a third, a fourth, a fifth. When x is 0.5, we get 2. When x is 0.2, we get 5. Okay, so this is it's a rational function that has a vertical asymptote at 0. Okay, here's my vertical asymptote, and so it grows infinitely. And we want to know what the area is from 0, so from this vertical asymptote to 5. Well, there's no geometry formulas to really help us here. And we're not really sure what to do with this asymptote because, right, so this keeps getting closer and closer. That's terrible. I'm sorry about that. But this continues to grow and approach the x-axis infinitely. So this is the first time in us realizing that this area might actually be infinite. Or we can say it does not exist, and actually we would actually say that that function, so 1 over x, is not integrable on that interval, on the interval from 0 to 5, because the interval contains a vertical asymptote. Alright, and finally we get to a word problem. Yay for word problems. This is where it finally might be getting interesting for some of you. We have a rocket that's launched at positive acceleration, and the velocity is recorded every 10 seconds. And so one thing that we might want to do here is just to visualize it, is I just made a little scatter plot. And there you can see every 10 seconds the velocity. Okay, so the here the x-axis is the time in seconds, and the y-axis here is the velocity at time t, and that's in feet per second. So first thing that we're being asked to do is to use a right-hand sum and a left-hand sum, so Riemann sums here, with 8 rectangles to approximate the integral. So remember, Riemann sums are our approximation tool. But what are they approximating? They're approximating the actual area, which is given by the integral. One of the first things that you might want to observe is what the delta x is. And we can observe that right here. So you might see that every interval, because we're recording every 10 seconds, that is our delta x. You could also do 80 divided by 10 to get, 80 divided by 8 to get 10. And that's our delta x. So that's how wide our rectangles are all going to be. So let's take a look at the right-hand sum first. So if I draw this, that would be my first rectangle. Okay, and so the height of it I determined at the first right endpoint, which is 10. Therefore, if I'm just looking at the table, which number will I be using as the first height of the first rectangle? That's right, I'll use 14. Okay, so you could almost say it like this. So you could say in this first interval here, from 0 to 10, I have 2 endpoints and 2 possible values, but I'm going to use the 14 as the height because it is on the right endpoint. What about my second rectangle? Well, my second rectangle is going to look like this. And so what is the height of that one? Well, here's my second interval right here. And what is the height of that one? That's right, it's 22. And so on. So I can continue drawing my rectangles, and what you'll notice is that the heights of each one of them, so the heights of all of, not good, the heights of all of these rectangles are given by the y values in the table. So the 29, 35, 40, 44, 47, 49 is the height of the last rectangle. Oh, that was good. Yep. So we used all of the y values except for the first one, because the first one is a left endpoint height. So if I'm writing out my Riemann sum, I'm going to add up all of those heights and then multiply by the 10, the delta x, and that gives me an approximate area of 2,800. What about the left-hand sum? Well, if I'm drawing a left-hand sum, my first rectangle is going to be different, because I'm going to determine the height here on the left of that interval, and so my height is going to be different. And so what's the height of that first rectangle? You guessed it, it's 5. What about the height of my second rectangle? Well, there it is. There's my second rectangle. And you'll notice that that's the same as the first rectangle was on the right-hand sum. That's right. So these are just all flipped across. And therefore, those same heights are being used all the way through. All of them except for the last one. So the second rectangle has height 14, and then 22, 29, 35, 40, 44, and 47. So here I'm using all the heights except for the last one, because that one is a right endpoint. My left sum then gives me an area of 2,360. So how is the actual value of the integral of the area compared with the previous Riemann sums? Well, if you're thinking like I'm thinking, you might say that since the function is increasing, okay, so you can see here that our velocity function is going uphill. Let me just draw something through those points. So because our velocity function is increasing, so let's probably do something kind of like that, then you will notice that all of the right-hand rectangles are overestimates. Okay, and that's specifically because the function is increasing. Okay, if it was decreasing, it would be the other way around. But because it's increasing, the right-hand sum is an overestimate, and the left-hand sum is an underestimate. So these are all below the actual curve. So what does that mean about our guess for the actual area? Well, it's somewhere in between. So I said about 2,600. Okay, that was my. Is that exact? No. If I had to guess, if it was closer to the overestimate or the underestimate, I would probably say it would be closer to the overestimate because of the curvature of the graph, and so that does that. So I'm actually probably really close, but we don't know. What does this number represent? Well, so if you're familiar with unit analysis and you're familiar with area, you might just take a second to realize that each square unit here on this area has measurements in 2 dimensions, and we said the x-axis is measured in seconds, and the y-axis is measured in feet per second. Okay, and so each of those, when you multiply seconds by feet per second, the seconds cancel out and you get feet. So that means that this number is actually our approximation for the distance that the rocket traveled during those 80 seconds. The last question is kind of interesting, and I gave you the formula for it. It says, use your answers to approximate the average velocity of the rocket on that interval. So not what's the velocity that the rocket went the whole time, because that's always changing, but on average. And here, you might be used to doing average by adding up a bunch of numbers and dividing by how many there are, but here it's different. Here we're going to take the total distance that the rocket traveled and dividing it by the total time it took. So if you use 2,600 feet for the distance and 80 seconds for the time, then you got an average velocity of about 32.5 feet per second, which is, well, that seems about average, right? So if I draw that over here, so if I draw like 32.5 here, that's about average. Okay. Problem 4. Here you are driving a truck, and to pass somebody you accelerate to 100 feet per second, and after you pass them and get back in the right lane, you go back to a safer 60 feet per second. And so that's what the diagram is showing. On what time interval is the velocity approximately constant? So I said that it looks like we get back to a constant velocity about after 30 seconds. So from 30 to 50. So this interval right here, that's about where we're going 60 feet per second constantly. Okay. Before that, we're still decelerating from 100 back down to 60. So what is the distance traveled on that interval? Well, you might remember learning that distance is rate times time, right? So distance equals rate times time. And so because I went 60 feet per second for 20 seconds, then 60 So our rate is 60, and our time is 20, and therefore I'm guesstimating that we went about 1,200 feet during that time. Well, if you take a second to explore, what you'll notice that is exactly the area of this rectangle. So the area below the graph is exactly, so it has exactly dimensions 60 by 20, which is 1,200. Okay? Ooh, interesting. So when the question part B says approximate the value of the integral from 0 to 30, what we're talking about is this area right here. There. Then you might start to think about, ooh, well, why would I want to find that area? Well, that might tell us something about the situation. But first, let's approximate it, right? So what I did is I said, let me cut this off here, and so this is 6 squares this way by 6 squares that way. So I have 36 squares, and then up here I have 1, almost 2. That looks like almost 2. Almost 3. Let's count it 3 with that extra part in the middle. And then this here maybe looks like about 3/4, and maybe this is another 3/4. So I said here about 4.5, right? 4.5 squares. But how much is a square? What does a square count for? Well, one of these squares, right? So one of these squares is actually 5 seconds by 10 feet per second. 10 feet per second. Sorry about my writing. So that means that each of these squares actually counts for 50 feet. So, there's, that part. So I found the total number of squares here. That's my total number of squares. So 36 plus 4.5 is 40.5 squares. But because each square counted for 50 feet, then I multiplied and got 2,025 feet. How else could I have done that? Could have used a right-hand sum and done some rectangles here, and there I would have had to kind of approximate. So a right-hand sum here with 6 rectangles. I could have done something like this, and then like this, and of course that would have been like an underestimate, right? And so I had to kind of estimate those numbers there, and that gave me something more like 1960, which is the year I was born. Just kidding, I'm gonna go to that. And I also could have done a left-hand sum, and that would have given me an overestimate, and so that could have given me a range of values. But the method that we used here for kind of approximating squares can also work. And finally, the last one. Here, this says write an integral for each area that's represented and approximate it if you can. So the first one we see is the area below the graph of 5 from 0 to 4, so that's our integral, and the area is 20. The next one, we have a triangle here. This is actually an absolute value graph flipped upside down. And so it's the integral from -4 to 4 of the rule of the function, right? So that's the rule is written right there, right here. And so I plug that in. And to find the area, I just used the area of a triangle formula. So the base is 8 here, and the height is 4. So 8 times 4 divided by 2. The third one is also a triangle. It's the area from 0 to 2 of 6 minus 3x. And again, the triangle area formula gives me 6. The third one is the area from 0 to 2 of x squared. And you'll notice here that we don't know the area of this shape here. This is curvy and it's not a circle, and so I had to approximate here. So I had to draw in some squares here and kind of eyeball. So there's one for sure that fits in there, and then that's kind of 2, as I said, 2.5, and that's good enough. The next one is a parabola, and so we want the integral from -5 to 5 of that rule. And here the approximation was a little bit more involved. Actually, what you could do is split it in half and only approximate half of it, and then double the answer, right? And so I don't know. Maybe you used 3 here and said, well, at 3, when x is 3, 25 minus 9 is 16, and so you made a little rectangle there. That's 3 by 16, and then maybe you made this into a triangle, so a 2 by 16 triangle, and I don't know, maybe you approximated what this was as well, and then double your answer. So I came out with about 230. And of course, in the last one, the integral from -1 to 1 of 4 over x squared plus 2. And here, just again by drawing some squares and stuff, there's 2. And then I said this is a little bit, it's probably a little bit more than 3 actually. If I would maybe change my answer now, because that's 3 right there, right? So that maybe should be more like 3.2. Looks like my house with snow on the roof. Alright, well, thanks for watching my videos. Sorry I couldn't be there in class to tell you in person, but maybe you like this better. I don't know, you could watch it at home sipping coffee and scratching your feet. But please make a note of any questions that you have. You can always email me with questions. You can bring your questions to office hours. You can bring your questions to class, and I'd be happy to address them. And don't forget to complete assignment 7.3 online so that you get more chances to practice these and to get feedback. See you around!